The Doppler effect is a shift in frequency of a wave due to the relative motion of the source or the observer of the wave. We're going to start with the source. We'll talk about the observer in just a second, right? So the idea goes back to diffraction, right? And if the source of the waves, right? Now I'm picturing instead of a rock, a duck, right? There's a duck on the lake, right? Right now, he's not moving. He's just sitting, right? He or she, depending on the duck, is just sitting, right? And because of the natural state of the water, he is oscillating up and down, which is creating ripples that are diffracting through the system, right? And expanding out in time. The energy propagates at the same speed throughout the water because the water is all the same. So the ripples are all evenly spaced apart.
You're talking.
There's a duck, and it's
up and down, and then it moves.
and now it's moving that way.
All right, one thing at a time. So first thing is that diffraction does happen, right? If a duck is on the water and it's oscillating up and down, the ripple patterns are evenly spreading in all directions. This is because the speed of the energy through the water is a set number because the water is all the same. Lee.
So the V equals O has diffraction.
V equals 0
Equals 0. Well, yeah.
is diffraction.
That's what I meant.
Right? We've already talked about this. The ripple pattern is what you observe. What's important to note, and really useful in the next diagram, is that the outside circle was created first, right? More circles are being created on the inside, the ripples are expanding outward, the outside ones were created first. Hold on. Yep, you got it. All right, so if I look in any direction, because of the fact that the speed of the wave through the water is constant, then the distance between the wave crests is a constant number no matter which direction I look, which should make complete sense, right? So if the wavelength between each individual wave is the same in any direction, then the frequency of the oscillations is the same in any direction. This makes complete sense because of the constancy of the speed through the water, right? What happens in the Doppler effect is that something is moving. Typically it is the thing creating the waves, right? So in this case the duck, but it could also be the thing creating sound, like an ambulance, right? Or it could be the thing creating the light, like a star, right? In all those cases, it is emitting energy at a constant wavelength and frequency, and the wave is traveling through the medium at a constant speed because the medium is the same on the outside. But if the source of the energy is moving, then we have a shift in frequency based on a change in wavelength, right? So what we have to imagine is that for this circle, right, the outside circle, the duck was actually over here, right? And so when it oscillated here, this outside circle was created, right? It is now expanding outward because of diffraction, but the next circle was then generated from a center that is slightly to the right. And then the next is slightly to the right, and then the last one is here, right? And so because of the fact that the source of the vibration is moving, right, then in the front, it is closer to the wave fronts of the previous vibrations. In other words, on the side where the source of the energy is moving, the wavelength is less than what it would be if it was stationary. Since the wavelengths are shorter, but the speed is the same, the frequency must be higher in order to balance, right, in our V equals lambda F formula. So when the source is moving towards the observer, the wavelength is shortened, the frequency is increased. So what you want to write down for the Doppler effect is that when they are moving toward one another, the wavelength is shortened and therefore the frequency is higher. Now it isn't a sliding increase. It doesn't keep increasing. That would only happen if the thing was moving faster, then faster, then faster, and faster, if it was accelerating. But if it's moving at a constant speed, the frequency just is a higher amount, right? And so they're evenly spaced, but they are closer together. And then the exact opposite's happening on the other side, right? The wave that was produced is propagating away from you while you are also moving away from it. So each subsequent vibration is now further spaced out than it would be if you were stationary. So the exact opposite statement is that when the source and the observer are moving away from one another, the wavelength is longer and the frequency is therefore lower. Right? It's the exact inverse of the previous statement.
Wait, when you say they're moving towards each other, is that the source and the observer?
Yes. Source and the observer. So what this means is it's absolutely possible for it to be the duck, right, moving, the source of the waves. But it's also possible that this would happen if the duck was stationary and you were in a boat moving towards it, right? Because of the fact that you would hit this wave, and then while you hit that wave, this one's moving forward, but then you're also moving forward, meaning that you would get to the next wave sooner than you should, right? The frequency would be higher even if the duck wasn't moving and you were, right? So as long as they are moving towards one another, the frequency goes up. The faster they move, the higher the frequency shifts, right? And obviously, if they're both moving, then relativistically, that's a higher speed, the higher the frequency shifts. So it's very possible for just the source to be moving, or just the observer, or both. Right? Evenly spaced from here to here is lambda. Right? This, behind the source, is spread out further. In front of the source, closer together. Even though in reality, in reality that's actually what's happening, right? That's actually what's happening. Because the duck is pushing in on the wave that it already produced, the subsequent waves are closer together. But because it is moving away from a wave it already produced, the subsequent waves are farther apart. That make sense? Yeah, that was a challenging question, but I think that does justice, right? All right, so obviously in water, right, if you go to a pond and watch ducks swim, I swear you will see this pattern, right? You can actually see it really easily with ducks swimming in lakes, right? This is really useful to think about what happens if we go faster than the speed of propagation of the energy through the medium, right? If I am able to go fast enough that I can keep up with the wave up here, right? Then I would be at the source of the original sound as more sound piled up behind me, right? If I can then go faster than that, I will then be in front of the sound that I'm producing, right? That's exactly what happens. If the machine, which most typically is an airplane, but there are a few cars that can do this, but not many, right? If the airplane can go faster than the speed of sound in air, right, which we know is 343 meters per second or 720 miles an hour, right, then the sound is actually behind the airplane. So what happens is you can imagine that it's compressing the waves and compressing the waves and compressing the waves. Well, it creates a huge amount of pressure, right, that piles up right on the front of the plane. When it gets past the plane gets past the wave, all of that pressure releases and you get what's called a sonic boom, right? A sonic boom is that pressure wave that is actually behind the plane. Now, when we think about sonic boom, we think of it as one, it's like an explosion that happens and then it's gone. But what you have to imagine is that that's a pressure wave that is actually propagating. So you hear it as one big loud sound, but that's as it goes past you. But it's still a big loud sound that is still propagating forward. So the example that I hope you're familiar with is the Concorde jet, right? Heard of Concorde jets? It's okay if you haven't. Normal jets are airplanes, commuter airplanes that you get in and you fly from here to Los Angeles, no big deal. You can fly from New York to London, right? It's like a 10-hour flight, something like that. The Concorde jet can fly faster than the speed of sound. It can fly from New York to London in 2 hours, right? Because it can go really fast. But you probably haven't heard about it because they were shelved, they were discontinued. Because when they passed the sound, the sonic boom was so energetic that the people living in the buildings on the ground were being damaged, or at least overwhelmed, by the huge sound wave that came behind the plane. Now the thing is, people in the plane have a great flight. Because if you've been in an airplane, you know that it's very loud. But if you're going faster than the sound, it's really quiet. The Concorde plane is super awesome to fly in because to you, the engines are a mile behind you because you're faster than the sound is propagating. So it's quiet. You can still hear people inside because the air inside is moving with you. So the sound that's happening inside the plane, you can hear. But the boom of the engines, the loud roar of the engines, ends up being behind you the entire trip. Right? And so you never hear them, so it's very quiet. But it's extremely loud to the people on the ground, so they discontinued it. Right now there is research being done. They're building Concorde planes with these ridiculously long needle-like noses, and that's to slice through the air with more aerodynamic, less friction in order to reduce the sonic booms. And hopefully, by the time you graduate college, those will be a thing, and we'll be flying to London in 2 hours. That would be amazing, right? It's coming back around. Hannah.
I had a teacher that went on one of them.
Yeah, cool. Yeah, so I mean, a number of people did get to fly on them, but it was so loud on the ground that they discontinued it. So what they did is they changed the rules and said that the Concorde jet could fly supersonic once it was above the ocean, but then the airlines found that it just wasn't financially worth it, right? Because the flights were still relatively long because they could only go really fast over the ocean. And so they just discontinued the program because it's too expensive, loud.
I have 2 questions.
Uh-huh.
One, is that called breaking the sound barrier?
That's exactly what it's called.
And then 2, is the sonic boom powerful enough to like break windows?
Yes, it is. So,
Wait, I have a
into,
question.
go ahead, LG.
So is it like, is that what it's like, you know, in Virginia Beach, has anybody ever been to Virginia Beach
Huh?
with the planes? Is it like louder than that?
No, it's like that, yes.
Okay, that's not that bad.
Well, arguably, and the faster you go, the louder it is, right?
Yeah.
Yes. Okay, so, I'm sorry, go ahead.
Couldn't
Oh,
we
I
just
didn't-
take off somewhere where people aren't?
Yes, and so they did try and change the flight pass, but now people are pretty much everywhere, and so it was just not financially viable, but they're working on it, right? In 2013, right, 2013, there was a meteor that actually crashed through the atmosphere of the Earth and landed in Russia, right? It landed in the woods in Russia, right? Because that's mostly what Russia is woods, right? And so it just crashed down. It didn't hurt anybody, right? But thank you to cell phones and street cameras, right? A number of people got it on camera. And this footage, right, shows and also illustrates exactly what we're talking about, right? So watch this.
Is that it?
Yep, see the comet in the air? Right, okay, now just hang out a second and check it out, right? There it goes. There it goes. Yeah, yeah. Wait, wait, wait.
Нихуя себе. Я сейчас подойду, подожди.
Wait. What do you think that was?
Building.
That's the sound. The meteor is going so fast that it flew past, hit the ground, and then the sound wave of it traveling through the air caught up.
It sounds like shattering.
It is shattering because behind them, all the windows in the building blew out.
Did it set off a car alarm?
Set off all the car alarms. Because it's a huge vibration that propagates behind the thing, right? So it sounds like an explosion right where you're at, and then the person next to you, it sounds like an explosion to them, and then it sounds like an explosion to the next person, and so on and so on and so on. Because it's a propagating energy wave that just keeps on going, right? Until, of course, the thing stops moving.
And then I put it, sorry, I'm not good at waves. Then it gets absorbed by like surroundings, right? Like
Exactly, which is the car alarms and the windows and everything else, right? When I was in high school, I got to go to the Air Force Academy to tour it, right? And while I was there, I was really surprised as to why there was plywood on all the sides of the freshman dorms, right? Have I told you this?
Yeah.
Juniors and seniors get to actually fly the jets, right? Because that's why you're there at the Air Force Academy. They do the one thing they are told not to do, which is buzz campus, right? So they buzz campus and they fly right past the freshman dorms, and the noise of the sonic boom as they go past blows out all the windows. And so they do that right before winter in order to freeze out all the freshmen. And then they can possibly get expelled because that's the one thing they're not allowed to do, right? But they do it anyway. Yeah. It's a common thing, right? It's like a tradition thing that they always do that, even though they're not supposed to. But it's a huge amount of sound, right? All right, so that's sound. Now, here's the thing. Oh, sorry. So I wanted to show you, because I could show you this in real life too, right? This is another tuning fork, right? This one is 523 Hertz, so this is an octave above middle C. Right? Right, you got that? Yeah.
Because
it-
there's more for the waves to.
It amplifies it by allowing the board to vibrate at the same frequency because they're touching, right? Amplification. Okay, so now that's not the point though, but this is a set pitch. It doesn't change, right? But,
Whoa.
does it sound different?
Yeah.
Because the thing is, you have to confirm that because it doesn't sound different to me.
What?
Because it's the same distance away from me the whole time. So all I hear is this. That's all I hear. But you hear something different, right? It sounds like it's wobbling. Because as it's moving towards you, the pitch is higher. When it's directly perpendicular to you, you're hearing the actual speed because it's not moving towards you or away from you, the actual frequency. And then as it's moving away from you, the pitch is lower, right? But it happens so fast that you can't distinguish between the three pitches, so you just kind of hear a wobble, right? But there's a great example of this because we live in Richmond, and you know RIR is the racetrack, right? Give me the sound. Race cars, right? Everybody does the sound, you know the sound, right? The issue is race cars go so fast that they start really far away and then they get really far away all of a sudden. So it's not just shifting frequency, it's also getting much louder and then getting much softer. And your brain, it happens so fast that your brain can't process it as three separate pitches. But that's exactly what it is, and I can show you that, right? Because NASCAR has like 1,000 cameras and microphones, right? So in the videos tab, right, on SaintsNet, I put these two videos. This first one is the Daytona 500 in 2016, right after the announcer says, "Gentlemen, start your engines," right? So all the cars are parked, and they are just sitting there, right? And so listen to this. That's it. It's just a loud rumble, right? Much, much louder than normal cars because they don't have mufflers like we have mufflers, right? So it's just a loud, loud rumble. It's a relatively low-pitched rumble because the engine is not spinning very fast, right? So first thing is that when it's stationary, it's a set pitch, right? All right, so if we go to moving cars, right? There's about 3 seconds of poor footage and then we get to the good one, right? Right. Right? Inside the car, while the car is running, the pitch is higher, right? Because the engine is oscillating faster than it was when they were just sitting. But it's still just one pitch. It's just wah the whole time, right? To the driver, like me in the middle of the circle, it's one pitch that isn't changing the entire time, right? But from outside the car, right? Inside the car, outside the car. Inside the car, one set pitch. Outside the car. Yeah. Now the problem is, right, these cars are going like 200 miles an hour, so it's happening so fast that we can't really process what's happening. But what is happening is while they're coming towards you, you're hearing a frequency that's much, much higher than the original wah sound, right? So it's more like wah, like that, right? But then when they're directly in front of you, right, they're perpendicular to you, so then you're hearing the wah, the middle, right? The actual sound. But then as soon as they get past you, right, then they're stretching out the wavelengths and the frequency is lower, right? And so it's high, middle, low, while also getting louder, getting softer. And because it all happens so fast, you can't process that that happens, and so we just hear it as meow, right? But it's important to note, just like resonance, it's stepwise function and not a sliding scale. Make sense? All right, so that's the Doppler effect. When we think about this in terms of other types of energy, right? We've done water and sound. The other type of wave that's most important is light, right? Light, there's two great examples. The first one is Doppler radar, right? Doppler radar in the weather, right? Any news channel uses the Doppler radar. What are they looking at?
The weather.
Weather, but more specifically, what's in the sky?
Clouds.
Clouds. They're looking at clouds, which are formed from pressure differences, so they're indirectly looking at pressure, right? But they're really looking at the clouds in the sky, right? On top of the weather station, on top of the news channel, right, or out in some location, there is a radar. The radar sends out light waves, which are radar waves, which are lower than visible light and exactly the same as Wi-Fi, right? It's the same functional characteristic. It's light that you cannot see. It spins in a circle and shines that light out into the air, into space, right? That light travels out, hits the clouds, and because it hits a new medium, it reflects, right? Just like any other energy that we would expect. If the clouds are not moving, the light comes back exactly the same as what it went out. But if the clouds are moving away, right, the light is actually stretched out in terms of wavelength, and so the color shifts, right? If you imagine Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, red is the lowest frequency, violet is the highest frequency. That's why ultraviolet is higher than violet and infrared is lower than red, right? Infrared, red, violet, ultraviolet, right? So if the color looks more red or comes back lower red shifted than it should be, we know that it's moving away. How fast it's moving away determines how much the shift happens, right? Vice versa, if the clouds are coming towards us, then the wave that returns is bluer, it is slightly higher frequency than the original wave, right? And we know that it's coming towards us and how fast. And basically what's happening is the output wave and the reflected wave, if they're both exactly the same, you get constructive interference, right? And the light is exactly the same. If it shifts one way or the other, then we have two frequencies that are really close to one another, and you get a beat frequency, and they can measure that, and that tells you how far apart the two things are, which tells you the shift, which tells you all the information you need to know, right? So Doppler radar uses the Doppler effect to tell what direction and how fast clouds are moving. This is how they track all weather, right? Hurricanes in particular, but thunderstorms, clouds in the air generally, right? The other form of Doppler using light is in astronomy, because stars emit light of a known color because of their composition of hydrogen and helium. How big they are determines what color that white light should be, right? Which is why our star is slightly more yellow, etc., etc. But when we look at stars through telescopes, some of them appear to be bluer than they should be, and some of them appear to be redder than they should be. How blue they are determines how fast they are moving, and the fact that it is bluer tells us they are moving towards us in space. Red shifting is the exact opposite. If the wavelength appears longer, the frequency is lower. That tells us it's moving away from us, and how much the shift is tells us the speed. We talked in universe fundamentals that the edge of the universe is expanding. We know that because light that hits the edge of the universe is redshifted, right? And we know that the acceleration of the expansion is increasing because it is more redshifted today than it was a million years ago, right? And so the edge of the universe is moving away from us faster than it used to be, and we know that from the Doppler effect, right? Make sense? All right, that's the basic concept. The formula, there's the formula. It goes with this. Looks confusing at first, but I promise it's not so bad. F prime equals F times the quantity, V plus or minus VO divided by V minus or plus, and that's really important, VS.
Why is that important?
I'll explain in 1 second. This is the Doppler frequency formula, right? And what it actually is 4 formulas shoved into one, right? Because it's possible to have the observer moving toward or away, and it's possible to have the source moving toward or away. And so instead of giving you 4 formulas and trying to remember which one's which, we've mashed them all together with some algebra, and then I've got one easy thing to remember, right? So first of all is definition of all the terms. F prime is going to be the shifted frequency, right? This is the new frequency due to the Doppler effect. F is the original. So that's the frequency of the sound or light if it wasn't moving, right? And then the rest of this is a proportionality based on the motion. V is going to be the speed of the wave, right? Which is a standard number through most mediums, right? So we know that the speed of sound through air is 343 meters per second. The speed of light is 300 million meters per second, 3e8, and any other speed I would give you. But those are probably the two that we're going to work with, right? Speed of sound and speed of light. So V, which is this term and that term, right? VO is the velocity or the speed of the observer. And then Vs is the speed of the source. Most typically, one of these two is 0. Most typically, right? You're in the stands watching the cars go by. You're the observer. VO is 0. That simplifies the top of the equation, right? But it's also possible, you can imagine that if a race car had just done the gentlemen start your engines thing and was sitting stationary and you drove by it at 200 miles an hour, you would hear meow even though the race car's not moving, right? The shift happens because you, the observer, are moving, right? It absolutely works. There is a small caveat, and the reason why they're separated is that how much it shifts is not exactly the same if it's the source or the observer. In other words, if the car goes by at 200 miles an hour, coming towards you, the frequency is higher. If you were going towards it at 200 miles an hour, the frequency would be higher, but those two numbers wouldn't necessarily be the same. And that's because the distortion is happening near the source or really far away from the source, right? And so the shift is what we call asymmetrical. That's why we have two different formulas, or two different variables. But the key to this is the writing of the operators, right? The plus and minus and the minus plus. In this system, right, if the observer or the source is moving towards, then you're going to use the top signs in the fraction. Top signs towards, right? So if the observer is moving the source towards the source, you use plus on the top. If the source is moving towards the observer, you use minus on the bottom in the denominator. And then the exact other way around if they're moving away from each other. So if they are moving away, then you're using the bottom signs. So the most complicated example I can think of is a police officer who's going to pull over somebody that isn't you, right? So he's sitting there clocking, right? Someone in front of you is speeding. They go by, the cop goes, oh, I'm going to get them, and they pull out, right? So now the cop is in front of you, going faster than you, right? Let's say you're going 80, they're going 80 miles an hour, you're going the speed limit 50, right? He turns on his siren. Because overall, you know that you're getting further away from each other, right? Because he's going 80, you're going 50. Then technically you know that the frequency will be lower because you're getting further apart. But in terms of selecting signs and variables, the observer, that's you, is moving towards the cop, right? Even though you're never going to catch him, you're moving towards him because he's in front of you and you are moving forward. So the observer moving towards would use a plus sign on the top, right? And then you put your speed in at 50 miles an hour. But the source of the sound in front of you moving away from you would be moving away from you, right? And so you would use plus on the bottom. That's as complicated as it could possibly be. Otherwise, most of the time, one thing is not moving and the other one is, and it's pretty easy to figure out. Does anybody have any questions? No?
Thank you.
Then we're done.